I think I've got it all. This laundry seems to pile up faster than I can throw it in the washing machine. You know, I've often wondered if I could save money without sacrificing cleanliness by washing my clothes in cold water instead of warm water. Once again, statistics comes to the rescue. Here's what I'm going to do. I've got a huge pile of dirty laundry here. I'll divide the load into 2 piles, wash one bunch in warm water, one in cold water, and see which works best. In statistical terms, my subjects are these lovely pieces of laundry, and my treatments are the 2 water temperatures. Now, when you're designing an experiment, it's always good to ask this question. Are the subjects different in any systematic way that might affect their response to the treatment? If so, the results might be unclear. What about our laundry? When I think about it, synthetics might very well react differently from natural fiber clothes to the different water temperatures. It's easy to see a solution. I'll sort each of my piles into synthetics and naturals. In statistics, we call this technique blocking. Each pile is a block. That means the subjects share a characteristic that might affect response to the treatment. In an unblocked experiment, I would randomly assign one basket of laundry to each treatment and record my observations at the end. In a blocked experiment, I would first divide the clothes into 2 piles, one for synthetics, the other for natural fibers. These are my blocks. Then I'd randomly assign them into treatment groups, one warm water and one cold water load for each block. Blocking and random assignment will allow me to get precise information from my experiment. In this program, we'll explore this concept of blocking and how it can help to reduce the effect of variation among experimental subjects. We'll learn another technique for getting accurate information about the world, sampling. We'll discover how a sample differs from a census and how both can be used to give us information about a population. No, this is not a detergent commercial. It's the data from my experiment. Here's what I found out. After washing each load, I inspected the clothing, rated each piece as either clean enough or still somewhat dirty, and compared the results. It turned out that the synthetics cleaned only slightly better in warm than in cold water. I might as well use cold water and save the money. But the natural fibers definitely fared better in warm water. Looks like I should continue using warm water on those clothes. This is a good example of how blocking before an experiment helps me get cleaner information. If my laundry loads had been mixed, the results for my 2 loads would have been similar, and I might have wrongly concluded that temperature doesn't make any difference. The technique of blocking is widely used to reduce the effect of variability between subjects. Blocking is especially useful in agriculture. For example, in the quest for the perfect strawberry.
Hi, George. How you doing?
Olivia, how you doing?
It's a nice sweet berry, and I do wish it had the juiciness of the rattan, but it doesn't. It just doesn't have it. The thing that we'd have to be careful...
These commercial strawberry growers are having a field day at the National Agricultural Research Center in Beltsville, Maryland.
These are for you guys to taste and eat. I think it lacks a little of the acidity that the rattan has that heightens the flavor, you see. But it's perfectly acceptable. In fact, one lady in Ohio said it was too sweet.
They're deciding the fate of dozens of different types of strawberries, sampling the results of years of research, determining which strawberries you'll be eating in years to come.
I need to get a better tasting honey. I've got to try a little more.
There are many things to breeding a strawberry that do not meet the eye. It takes about 10 years from the time that a strawberry seed is planted until an ultimate variety, not necessarily from that seed, makes it into the market. During this time, there are many screening procedures that eliminate the berries that do not perform according to certain standards.
The quest for the perfect strawberry begins here with a selection of parent plants, chosen on the basis of characteristics which are promising, but which need improvement. These plants are grown over the winter in greenhouses, and in the spring they are strategically bred with another parent plant. A new generation of genetically improved fruit develops, whose seed is collected and dried. These seeds will be germinated and subjected to a variety of diseases. The plants that prove themselves disease-resistant in this first trial are cloned and later planted outside for further tests.
The next year we go in the spring and evaluate them for fruit. When we evaluate them for fruit, we're looking first of all for the quantity of the fruit, then the uniformity of its appearance, its color, its firmness, its texture as you eat it, any aromatic compounds, the toughness of the skin so that we know it would endure handling, and of course, most important, the flavor of the berry.
Once the plants have made it this far, the researchers have a lot of time and resources invested in them. So if the plants develop a virus at any time during their journeys between field and lab, a delicate operation is performed. A microscopic piece of the stem is cut, and the plants are recloned, this time virus-free. The strawberries are replanted in the field, and again evaluated to make sure the virus has been eliminated. They're now ready for the final trial. They must compete head-to-head with the standard varieties, those strawberries which have already proven themselves in the marketplace.
And we try to do that by employing a statistical design called a randomized complete block design. And what that means is that we actually have 4 experiments within the lines of this orange tape. We have each of the 33 entries entered once, and within that section or replication, each of the entries is randomized so that it can land at any one space. In other words, the soil can be sampled from one end of the field to another.
The reason for designing the experiment as a randomized complete block has to do with variation in field conditions. But let's back up for a minute. These long horizontal rows are the blocks, almost like separate experiments. Each type of strawberry plant is randomly assigned a row within each block. We then compare the strawberries from the new plants with the old varieties planted in the same row. Dr. Galletta could have taken the same field and just randomized the selections once without blocking. But we know that the conditions in any field vary from spot to spot. What if one part of the field had slightly inferior soil or drainage problems? The researchers would have no way of knowing if a plant's poor performance was due to this natural variation or to the plant itself. But in our blocked experiment, if one selection performs poorly in one block but excellently in the other 3 blocks, we would suspect that some unknown natural variation was at work. What Dr. Galletta would probably do in that case is test the selection that had uneven results in another randomized block experiment. Now let's return to the strawberry fields and look at some preliminary findings.
The results of the randomized trials are evaluated at the end of the growing season, when the unnamed, numbered selections are compared with the named standard varieties.
This one, for example, is Maryland US 5283. This is one of our late fruiting selections that we're looking at for the very first time. You see it has extreme beauty of fruit, quite a good amount of fruit, a very nice healthy bed, and it's just ripening. Just a few of those berries are red. As I remember it from last year, it was quite aromatic and very good to eat. Very firm and solid. One of the berries that we might contrast the new 5283 with would be the Kent variety, which was developed in Nova Scotia and has proved to be a late maturing, very hardy, very productive berry. We have weighed and measured this one, and we will weigh and measure that one, and then we'll compare. And normally we name them if they're better in 3 or 4 traits. We've rated the berry as exceptional in quality, average in flavor, exceptional in all the other characteristics.
And so the process continues. Feedback is gathered from the growers, and decisions are made about which selections will be planted in next year's randomized block experiments. And if all goes well, after 10 years of enduring the rigorous trials of Buntsville, this strawberry might end up on your supermarket shelf with a name of its own.
You can see now how the statistical design of experiments involves more than just the key ideas of randomization and comparison. We've seen that blocking can make comparison more precise by reducing the influence of variation among experimental subjects or testing conditions. Until now, we've looked at experiments that involve only a single variable, different varieties of strawberry plants, for example. But experimenters are often interested in more than one factor. Suppose we wanted to see how a single strawberry variety performed under different treatments. We could start by testing the plants with different amounts of fertilizer. Since the only difference in outcome should be due to the fertilizer, we call this a single factor experiment. Now suppose we also wanted to look at how the plants performed under 3 different light levels. The design would now look like this. Each combination of factors results in a single treatment. The number of possible treatments multiplies rapidly as you add factors, for example, the presence or absence of insecticide. But no matter how many factors we have, the same principles of randomization and comparison apply. Sometimes we merely want to know the way things are without changing anything. For instance, suppose we wanted to know what percentage of supermarket chicken is contaminated with salmonella bacteria. What percentage of Americans smoke marijuana? How many people are homeless? An experiment wouldn't help us find the answer. We could answer these questions by testing every chicken for salmonella, asking every person if they smoke pot, and counting every homeless person. The name for such counting is a census, a count of every item in a population. That seems like the most thorough way to get information, but as we'll see, taking an accurate census isn't as easy as you might think.
One of the more radical ideas put forward in the Constitution was that of a nationwide census. Each citizen was to be counted every 10 years, and representatives to Congress would be apportioned according to the population of each district. This system was fundamental to the one-man, one-vote concept of democracy. The first census conducted by Thomas Jefferson counted almost 4 million people. But counting everyone proved to be an impossible undertaking, and many people were missed. The census has been taken every 10 years since then, and overall accuracy has been improving.
Evening, gentlemen.
Who is it?
I'm the official census taker. You mind?
But as this 1960 film illustrates, there have always been certain segments of the population who are difficult to count.
Now, Peter.
Gentlemen, the law requires that every person be enumerated at least once every 10 years.
Barbara Baylor is committed to making sure the census counts everyone. She is former head of statistical research at the Census Bureau and is now executive director of the American Statistical Association.
The undercount problem, though, was recognized very early in the census. In fact, George Washington recognized that there was an undercount problem in the very first census. It was not ever really seen as a real difficult problem as long as it was thought that everyone was undercounted at the same rate. It was found then, when we got more sophisticated statistical techniques, that the undercount was not uniform, that it was primarily in the minority communities.
The undercount in the last census ran about 6% for minorities, that is blacks, Hispanics, and Asians, and less than 1% for whites. So you can see there's a significant shift. We're talking about hundreds of thousands of people. And so it's based on that we have to truly understand that the undercount cuts in to participation in the political process of minorities, because if the count is not right and we lose them, then we're losing representation.
In addition to representation, minority communities are also losing their fair share of the more than $30 billion in federal funds granted on the basis of census data. Funds that are used for social services, for community infrastructure, for hospitals and schools. Before we can evaluate solutions to the undercount problem, we have to understand how the census is conducted. The first and most important step is the mailing of a questionnaire to every household in the United States. About 83% of the questionnaires are returned to the Bureau to be be processed within the allotted time. A census taker must visit those households that do not respond by mail. Over 300,000 census takers are hired for this difficult task. It's here that minorities are often missed.
There are lots of reasons why it's difficult to count minorities. One is the census procedures themselves are devised by people more or less like myself, middle-class people who think about other people living in similar circumstances. It's very hard to think about the homeless and how they might be counted, and we know we don't do well with the homeless. There are people who do not want to be counted. People who are in the country illegally cannot see that, even though they're promised confidentiality, that the Census Bureau won't turn around and give that information to the Immigration Service.
And then the last set of reasons is just apathy. They have been promised many things by the government in the past. Some of them have not happened. They're turned off a bit to society, and they're really not moved by another government agency coming out there and saying, we're here to do something good for you. Those are difficult things to overcome. These are not procedural errors in the sense that the address is not on the census list or anything like that, or the questionnaire did not arrive at the house. They're people choosing to leave themselves out.
Stand right up for who you are. Stand up right now. Stand up and be counted.
Barbara Baylor and other experts have proposed statistical adjustments to correct the undercount. But for now, the Census Bureau will continue to rely on community outreach in attempting to achieve the goal of the Founding Fathers, full representation for everyone in the nation.
We've seen that a census isn't as easy or as accurate as it might at first seem to be. Still, it's the only way we can get the kind of detailed, street-by-street information the government needs to draw political boundaries. But for most other kinds of information gathering, there's an alternative to a census. It's called a sample. The idea is simple. A sample is a count or measure of only a representative portion of the whole. It's a bit like tasting one spoonful of soup to see if the whole batch is edible. The entire group we want information about is called the population, whether it's soup or grapes or ball bearings or people. The small part we look at is called the sample. Now, as you might expect, a sample is only good if it truly represents the entire population. It's my job, and the job of statisticians in general, to ensure that a sample is truly representative. One of the keys in doing this is to replace human selection of individuals with some random process, such as a table of random numbers. Random selection eliminates the possibility of conscious or unconscious bias in the choice of our sample. Why is that important? Here's an example. In 1987, Cher Hite published the book Women and Love, which detailed women's attitudes on a wide range of subjects. She based her book on responses to about 100,000 questionnaires sent to women's and church groups around the country. Only 4,500 women, 4.5%, responded. One of her findings was that 70% of women married more than 5 years were having extramarital affairs. Hite's methods have been criticized for several reasons, but the most troublesome from a statistical point of view was her reliance on voluntary response. Only those women who cared enough about Hite's subject to fill out her very long questionnaire were included in the study. That's a form of bias, a systematic distortion of outcomes. It's unlikely that such a group of self-selected women is truly representative. As we'll see, obtaining a random sample of human beings can be tricky. The task is easier when we're dealing with inanimate objects, like potato chips.
Looking to add some more excitement to your celebration? Try barbecue and sour cream and onion flavored Lay's potato chips. There's never a dud.
How can a major potato chip producer like the Frito-Lay Company fulfill such a claim? And when we open a bag of chips, how can we expect consistent appearance and taste? Whether you're manufacturing potato chips or any other product, a key ingredient of quality and reliability is sampling. Outside a Frito-Lay plant, like this one in Killingly, Connecticut, the sampling process begins as soon as a truckload of potatoes pulls up to the receiving dock. Willie has driven this load in from Florida. Once he checks in, the receiving department has to decide whether to accept the shipment. Every truckload carries about 45,000 pounds of potatoes, so the inspectors can't look at every one. Instead, they take 5 samples, filling 30-pound buckets at 5 different points down the length of the truck. Looking at every potato would be impractical, and it would also produce too many mistakes due to human error. Frito-Lay can get better information by studying the 150-pound sample. First step, the inspector randomly selects 40 pounds of potatoes and punches a core through each one. The hole down the middle will make it possible to spot the samples when they undergo a cooking test. Now 10 more pounds are set aside, leaving an even 100 pounds on the table. The inspector searches for internal defects, green edges, mechanical damage, and other flaws. The defects are weighed, and if the sample percentage is too large, the whole load must be rejected. Meanwhile, Rita has peeled the cooking samples, so she can toss them directly into the slicing machines. Thanks to the telltale holes, the sample chips can be distinguished from all the other ruffles coming down the line. Rita plucks them out and hands them over for testing at a mini laboratory right on the plant floor.
Willie got here early, but they had to put all the potatoes on the truck, yeah.
Willie is still waiting for the verdict. Less than 45 minutes have elapsed, but Rita has the results from the cook sample and the inspection data. Everything meets specs, so based on a sample, Frito-Lay will accept Willie's shipment.
Nice lot of potatoes. You can go ahead and weigh up, put your truck on number 2.
A hydraulic platform lifts Willie's truck, and this lot of potatoes is on its way. Precise sampling procedures using just 150 pounds of potatoes enable the receiving department to approve the entire 45,000-pound shipment. After washing, potatoes tumble into the peeler, and then into the slicer. Drums like this spin inside the slicer, forcing potatoes against the blades. A serrated blade makes ridges for ruffles, while a straight one cuts regular chips. Out of the slicer and into the fryer, hot oil and a little salt turn the potato slices into finished ruffles. Once every 15 minutes, Karen collects 3 samples of the ruffles for quality control analysis. She divides up the samples for a series of tests. Appearance defects are measured. Spectral analysis determines if the chips have been cooked to the proper golden color. Part of the sample is put into solution to measure salt content. To create the solution, chips have to be ground up. That's another advantage of sampling. If every chip were tested this way, there'd be none left to sell. Karen's supervisor gathers a sample of 10 uncooked ruffle slices and measures their thickness. She tracks all the tests on a control chart, a time series record of sample data. Taking samples frequently allows the staff to adjust the production process before problems become serious. The cooked chips cruise out of the production area and into packaging. A few ounces fall into each of these automated bins. When the bins add up to the proper package weight, the chips are released. Packages are stamped with the plant number and other coded data. The actual filling process is hard to see for our ruffles. Doritos, with their transparent bags, are easier to follow. Regular sampling procedure is as important in packaging as in production. Here, an inspector measures a sample of 4 bags to make sure the net weight is satisfactory. Even when they've been tucked into shipping cartons, the ruffles are still subject to sampling. It's crucial to make sure no underweight packages leave the plant, so cartons are randomly selected off the packaging lines for a final check before they're loaded onto trucks and driven to Frito-Lay distribution centers. And even after the local route trucks make deliveries to supermarkets and corner groceries, Frito-Lay continues to rely on sampling. All across the country, professional shoppers go out each week to purchase 2 bags of every product with different code dates. These ruffles and the other shopper samples are sent to company headquarters in Dallas for testing and comparison.
Hi, how are you?
On all packages of Ruffles and the other Frito-Lay potato chip products, you'll find a list of ingredients. The only one missing is the most essential ingredient in the recipe: proper sampling.
In this program, we focused on two ways to obtain reliable information. We saw how blocking is used to reduce the effect of variation between subjects or testing conditions. And we learned that we can draw sound conclusions about a population by studying a tiny sample. Next time, we'll explore sampling in more detail. By that time, of course, I'll have another 4 loads of laundry to do. But at least I'll have the satisfaction of knowing I've gotten it clean without wasting money.
If you would like to further your studies in statistics, we recommend the accompanying course package, which includes the text Introduction to the Practice of Statistics, as well as a study guide linking the programs to the textbook. The complete package is available for $69. To order yours, have your Visa or MasterCard ready and call Toronto 445-5333. From outside Toronto, call 1-800-663-1800.
We had an abusive situation. Someone called the police. Police arrived and they started their initial investigation. If medical assistance was needed, that was called. We removed the abuse.
Responding to victims of abuse is designed to make police officers and community workers more aware of victims' experiences. The accompanying workbooks on child abuse, wife assault, elder abuse, and sexual assault can be ordered by calling the numbers listed on your screen. Then tune in Thursdays at 8:30.
It's the same flat country everywhere.
In the 1890s, a wave of European immigrants arrived on the Canadian prairies.
Baby? You alright?
Janek, Mrs. Kovac, just paper.
One day we have toilet paper also.
Many built their first house from the same earth that would grow their bread. They called it a soddy.
What effect has religious dogma had on the current environmental crisis? The Science Edition presents a documentary and a discussion on religion and the environment tonight at 9.
This is TVO.
Welcome to TVO Home Studies. Next, we present Against All Odds, a university-level statistics course. The accompanying text, Introduction to the Practice of Statistics, is part of the course package. It provides contemporary instruction on data analysis. You'll also receive a study guide, which links the programs to the text and includes reading lists, problem assignments, a self-test, and sample examinations. At the end of the program, we'll tell you how to order the course package. Now, Against All Odds, Inside Statistics.
Well, I think I see the light at the end of the tunnel. I've been spending the past week designing a nationwide opinion poll on government funding of daycare. Surveys like this one play an important role in our society, in shaping public policy, in charting or even changing the course of an election. In this program, we're going to learn how to design a complex survey like this. We'll see how to improve the accuracy of a survey by using a stratified random sample. We'll learn how to avoid the kind of errors that can plague samples of human populations. And we'll see how sample size affects the spread of our sampling distribution. Sampling, whether of opinions or potato chips, produces numbers, educated estimates about a specific situation. These numbers, calculated from a sample, are called statistics. We have to be careful to distinguish between a statistic, which is an estimate based on a sample, and the true value that describes the entire population. The true value in most statistical problems is unknown. That's why we work so hard to find an estimate. This true value is called a parameter. For my survey, the actual percentage of the U.S. population favoring government subsidy of daycare is a parameter of the population. I'm going to take a sample from that population and find a percentage of those who want daycare subsidies. That statistic will be my estimate of the unknown population parameter, the percent who favor subsidies. Just remember the first letters. Parameters come from populations and statistics come from samples. Now, I could just take a simple random sample for this survey. You know, draw names of U.S. residents from a hat. That's what we mean by the term simple random sample. Well, I wouldn't get very far that way. Not only would I need a list of the entire adult population of the country, but I'd need a hat the size of a swimming pool. Instead, I'm doing what national sample surveys usually do. Take the sample in several stages. First, I'll select a random sample from the country's more than 3,000 counties. For the second stage, I'll take a random sample of towns within each county. And finally, randomly select individual households in each town. Now, if that's all there was to designing a good national sample, I'd be all set. Unfortunately, it's not so simple. Most of the 3,000 or so counties in the U.S. are rural. If I took a sample of, say, 50 counties, I could easily wind up without a single urban county. That would not give me a very representative sample of the country. So I'm purposely going to select a sample of the most populous counties and include them in the first stage of my survey. Then I'll take separate samples of suburban and rural counties. This process of dividing a population into units that we know are similar in some way is called stratification. It's a very similar concept to blocking in an experiment. In both cases, we're dividing our population ahead of time in order to produce clearer results. Sampling a population in strata is extremely common, and it's used in some rather interesting ways.
Fishing is one of America's favorite hobbies. There are over 17 million recreational fishermen in the U.S. looking for hundreds of different kinds of fish. These fishermen are looking for bluefish.
They're out there, you just gotta get lucky to catch them. Well, Sunday we were here, we caught about 3 or 4 of them. We're happy. There's this guy who caught 9 of them down there.
Is 9 bluefish an average catch? And if so, is the bluefish population in trouble? To assess the impact of recreational fishing on fish populations, a survey is being conducted for the National Marine Fisheries Service, the first nationwide database of its kind.
The intent is to get an estimate of how many fish are being caught of each species so that we can use that to assess the stocks and determine whether they're healthy or whether they're being overfished.
As the boat heads towards open ocean, Mike McCann, an interviewer for the survey, collects preliminary data on a randomly selected group.
Research. Is there a particular type of fish that you're going to be fishing for today?
Whatever I catch. In the past 12 months, how many days have we saltwater recreation?
Mike finds out all he can about the fishing habits of those on the boat.
Do you have a phone?
Then the boat drops anchor, and the fishermen go to work. The survey monitors both the size and amount of fish caught of each species. Yep. If fishermen are catching fewer of a certain type of fish than in previous years, this indicates that the species might be in trouble and that protective measures might be needed. The second part of the survey takes place on the way home, when Mike assesses catch size and weighs and measures a random selection of the fish caught.
Did you catch any fish for us to look at? Got a nice cod here.
If all the interviewers had to do were to take a simple random sample of fishing sites in their area, this would be a relatively easy survey to conduct. But fishermen who fish in different places catch different types and different amounts of fish. Our party boat caught cod and redfish. These pier fishermen are looking for bluefish, and private fishing boats might be looking for tuna or haddock. Since the purpose of the survey is to get an accurate sample of all species caught, these known differences have to be taken into account, and this is where stratification is useful. For each of the three strata, party boats, shore fishing, and private boats, a separate random sample is taken.
We know that there's going to be more variability if we make just a simple random sample across all modes, and the purpose of stratification is to obtain a better estimate and control your variance on that.
Because the survey is stratified, information from each mode of fishing will be included in the database. Biologists and local marine planners can thus use the data to protect future generations of fish and to please future generations of fishermen.
The principles of stratification and randomization that are used to find out about fish catches also apply to sampling people's opinions. Here, booby traps are everywhere, and you need to be aware of them. For example, in 1936, the magazine Literary Digest predicted that Alf Landon would beat Franklin Roosevelt in that year's election. The magazine based its prediction on 2,376,000 questionnaires, a huge sample size. The magazine drew the survey subjects from lists of automobile and telephone owners. At the same time, a young man named George Gallup used a sample of 50,000 people and predicted that Roosevelt would win with 56% of the vote. Gallup's prediction was ridiculed as naive until the election. Roosevelt won with 62% of the vote, and Gallup's career took off like a rocket. The problem with the Literary Digest sample was the list was weighted in favor of those with enough money to buy cars and phones, a much smaller portion of the population in the 30s than it is today. The poll missed the large pro-Roosevelt sentiment among lower-income voters. This sampling design systematically missed a portion of the population, so it's an example of bias. Sometimes it's not the sample, but the way a poll is administered that's the problem. Let's look at some mistakes that are easy to make and that should be avoided at all costs.
Doing a survey on the arms race.
The wording of a question can easily influence people's answers. Listen to how the same question can be asked in radically different ways.
The Soviet Union now has a slight edge in nuclear weapons over the United States. Do you support or oppose a freeze on nuclear weapons? I don't trust the Russians. So you would oppose a freeze? Correct. Thank you very much. The nuclear arsenals of the United States and the Soviet Union contain about 50,000 warheads. Do you support or oppose a freeze on nuclear weapons? Support. Thank you. We're doing a survey on marriage. You don't believe it. You don't believe it.
Responses may also be suspect if people think others are listening.
If you had to do it over again, would you marry your spouse?
Oh, absolutely.
Yeah, you would. Okay. Thank you.
Thank you. And of course, people may voice opinions on subjects about which they know nothing.
We're doing an opinion survey on politics. Do you support or oppose the U.S. aid to the rebels in Eastern Alpha Centauri?
If you've never heard of the Alpha Centauri rebels, don't worry, they don't exist.
Quick question.
Finally, the appearance of the interviewer may influence the response.
Personal preferences and appearance. Do you think you can trust men with mustaches?
Yes. The moral here is clear. Sampling has to be done carefully, especially when humans are involved. Let's look now at one of the top survey research institutions in the country. We'll see how they conduct their surveys and what they've learned about American attitudes and beliefs.
In general, do you favor or oppose the busing of black and white school children from one school to...
In the last 15 years, what has been the trend in Americans' attitudes towards racial integration?
Favorite.
Okay.
On race relations, tremendous liberalization. Approval of busing to promote racial integration has gone up steadily through the period.
Now please tell me if you agree or disagree with this statement. Most men are better suited emotionally for politics than are
What has been the trend in attitudes towards women?
Disagree.
Okay.
Feminism is doing very well. Approval of women working, approval of women's involvement in politics, things like that have gone up steadily.
Do you approve or disapprove of a married woman?
What has been the trend in attitudes towards sexual behavior?
Enormous increase in tolerance of premarital sex. We have a tremendous liberalization there. On the other hand, for extramarital sex, no change, very high disapproval.
I'm going to name some of these problems.
What is the process that takes us from the opinions of individuals to these sweeping conclusions about national trends? One of the best places to see this process is at NORC at the University of Chicago, a leading social science research institution. NORC conducts national surveys on such topics as education, health, the family, the labor force, and the social fabric of America. Through the General Social Survey, NORC has been tracking the changing attitudes and beliefs of the American population since 1972.
First, the
core of the General Social Survey, or the GSS, is 1,500 personal interviews conducted nationwide every year. A careful survey design makes it possible for these 1,500 to represent a population of more than 200 million.
Once you make sure that your sampling techniques establish an equal chance for everyone, then that is the underlying premise which assures that the 1,500 will be representative of the 200 million Americans, because all of the 200 million Americans had an equal fair chance of being in the sample.
As we start up here, Susan,
The first step is to stratify all counties in the U.S. by region and by urban-rural classification. Stratification ensures that all regions will be represented and that there will be some cities in the sample. Then the samples are taken in stages. First, a random sample of counties within each stratum. Next, a random sample of neighborhoods. Then a random sample of blocks. Once the sample selection is down to the block level, NORC checks a census list to see if any residences have been added or taken away. The list is updated, and eventually a final selection of households is made.
Are there any situations you can imagine in which you would approve of a man punching an adult male stranger? And tell me what you're thinking as you answer the question.
The next step is questionnaire design. To see if people are understanding the questions the way they're intended, think-alouds are conducted to let researchers into the thought process.
I wouldn't approve of it at all, period. But if a situation came up like you saw someone being hit, and you would say to yourself, why are you hitting that individual? And you walk up, pow! Okay, that, I don't necessarily approve of it. But if it calls for a punch, then give it to him.
The response process is a complicated thing. People have to, interpret the question correctly in the way that the researcher wanted to interpret it. They have to retrieve from memory whatever information is relevant to answering the question. Often they have to combine the information into some kind of overall judgment, and then they have to report an answer. And things can go awry in each of those steps.
How many long-distance calls have you made in the last month? Tell me what you're thinking as you answer this question.
Once in a while, I'll call my brother in Michigan.
By having people talk aloud as they answer survey questions, you can detect some of these mistakes, and you can also get a better sense of how people go about trying to answer the question, and therefore improve how you phrase the question.
I'm going to name some of these problems, and for each one, I'd like you to tell me whether you think we're spending too much money on it, too little
How
money.
a question is worded can be crucial.
Welfare?
I think we're spending too much on welfare.
In a questionnaire experiment, NORC found that only 30% favored spending more for welfare, but 60% favored spending more for assistance to the poor.
Assistance to the poor?
Too little. When you're dealing with the issue of public assistance, we found that it's a very complex issue with a lot of different images brought to the public mind. And you have to take it as not one simple question, but a whole series of questions that tap these different dimensions.
You sort of act like a tape recorder. You're just recording what the respondent is
No matter how carefully the questions are designed, unless the interviewer asks the questions without bias, the response data will be invalid. One difficult situation for the interviewer is when a respondent answers don't know to a question.
It's a lazy don't know, what we call lazy don't know. And they just need a minute to think. And if you probe that and say, well, just take a minute to think about it, then they do come up with an answer.
What about an embarrassed don't know? Say it was something like, how many times have you had sex during the past year? And you know that the person, if they don't know, they've got a pretty good idea of how many times.
Okay.
But they answer, don't know.
Yeah.
Then is it okay to probe and say 20 times, 30 times?
You suggest an answer?
Well, is it? No?
No,
Okay.
absolutely. That you never suggest an answer. You would probe.
Another important lesson is how to remain neutral in tone of voice, response, and body language. Role-playing helps illustrate this point.
Now, Miss Brandon, during an average week, how many drinks would you say you consume?
Oh, about, I would say 20.
Really?
Oh, no, really, only 2 or 3. I was just kidding you.
Okay.
Okay. Do you see how she changed her answer? Yeah. She knew that interviewer was shocked. It would set the mood for the rest of the interview, and you obviously would not get honest responses. This was a real example of interviewer
Another role play? How to deal with a reluctant respondent.
Hello, this is Lee Brandon with NORC at the University of Chicago.
Yes.
Okay. University of Chicago. Now, I'm here. You received a letter recently that I would be calling on you to interview you, and I would like to come in and interview you.
I don't have time. There's some people next door who they sit around all day and they have nothing else to do, and I'd rather you go over there. Please don't bother me right now.
Well, they're not the person that was selected for this interview. So you're a very important person to us, and it's not your neighbor. She might fall into a sample and a survey another time, but she is not the one that was selected for this survey. It's you that we need.
Hello, I'm Craig Hill from the National Opinion Research.
Despite the interviewer's best efforts, generally about 20% of the respondents refuse to participate or cannot be found. This means that in order to reach their target of 1,500 respondents, NORC must include over 2,000 respondents in their initial sample.
Do you favor or oppose the death penalty for persons convicted of murder?
I oppose it.
Okay.
It is the combination of statistically sound sample selection, careful questionnaire design, and skillful interviewing that make it possible to identify a slow but unmistakable liberalization of opinion on many issues in America.
American society is changing very slowly but very steadily. A rule of thumb, our questions will move about 1 percentage point a year. Well, we've been at it 15 years now, so the American population for many of our items is 15 points from where it was where we started out. And it's a bit of a puzzle because we have this impression that the world is changing wildly around us. Actually, it isn't, but it is changing very steadily.
NORC has been able to track very subtle changes in public opinion. You might be wondering how we know that these changes are not just due to natural variation. I mean, what if we asked another 1,500 people? Wouldn't we get slightly different responses? This brings us to an important point. Since the results from random samples vary to some extent from sample to sample, our result will only approximate the true parameter. But since we can accurately measure this variation, the answers we produce with sampling are of the highest quality. The key question in any estimate is, How much are we off? Let's suppose I'd like to know what percentage of these beads are dark. Since I went to the trouble of counting the beads out, I know the actual value. It's 20%. That's the parameter we're going to estimate by sampling. But we'll pretend this is a real situation and we don't know the population parameter. I'm going to take a simple random sample of 50 beads with this special scoop. All of the beads have the same chance of falling into the holes. Now let's try it once. Okay, I've got 13 dark beads there, so the statistic we're looking for, the percent of dark beads in the sample, is 13 over 50, or 26%. Let me dump these back and take another sample. This time I got 8 dark beads, so that's 8 over 50, or 16%. 2 samples, 2 different answers. If we didn't know the true value, how would we know which value is closer to the truth? Well, let's do some more sampling and keep track of the results with a histogram. Phew, that was a lot of work. But here we are with the results of 1,000 samples, neatly summarized in this histogram. This is the sampling distribution of our statistic, and it contains important information about our sampling procedure. Now, we've seen this shape before. It's regular, very symmetric, and roughly normal with no outliers. More importantly, look at where the center is, 20%. How about that? Still, there's a lot of variability. In fact, the standard deviation is about 0.057, or almost 6%. Let's think about this for a minute. Although the statistic varies from sample to sample, in the long run the variation follows a regular pattern. So regular we can describe it as a normal distribution. And you can see immediately that the center of the distribution falls on the population parameter. That's because our carefully randomized procedures have eliminated the bias. Precision is the term we use to describe how close our sample results cluster together. Statisticians always seek low bias and high precision. That precision is intimately related to a familiar concept, the standard deviation. Let's see how it works. Here's the smooth distribution of our bead sampling demonstration. You recall that our mean was 20% and our standard deviation was 5.7%. The 68-95-99.7 rule says that about 95% of all our observations will lie within 2 standard deviations on either side of the mean. In our example, that means 95 out of 100 samples in the long run will give an answer between 8.6% and 31.4%. That's a big spread. One sample of 50 beads isn't very trustworthy when the results can be so variable. What does this mean for a statistician like myself who is asked to design an accurate survey? How can I be confident of my results if I can only afford to do a single nationwide sample? Well, let's go back to our distribution and see what happens when we increase the size of our sample. Let's say that instead of drawing 50 beads each time, we drew 200 from a hypothetically large population of beads. The result would look something like this. The histogram would still be symmetrical around the 20% parameter, but the spread would be narrower. The standard deviation in this case would be only 2.8%. Now let's increase the sample size to 800. The standard deviation shrinks, and our precision improves again. By the time our sample grows to 1,500, our standard deviation is only 0.01, or 1%. Twice that is 2%. So now 95% of all sample results will lie within 2% of the truth. A result so precise that many pollsters, including those at NORC, usually question about 1,500 people for their surveys. Notice, it doesn't matter how large the population is. Although it may seem surprising, it's the size of the sample that determines precision. The same size sample gives you the same precision, regardless of the size of the population. The sample size of 1,500 puts us within about 2% of the true mean in 95% of all samples. That's for a simple random sample, like the beads. The actual number will change a bit if we use a multi-stage stratified design. Now, we still can't say exactly what the size of the error is in any one sample, Despite our best efforts, we could just be unlucky and have an unrepresentative sample. But we can say this, that 95% of all samples of a given population will give results within 2 standard deviations from the mean. This is called the margin of error, and that's how the precision of a random sample survey is measured. We'll be investigating this concept more in future programs. In this program, we've explored one of the most powerful yet tricky statistical tools we have for getting information, sampling. Good sampling relies on randomness, a topic we're going to explore at length in our next few programs about probability. In the meantime, I've got to finish this survey design or I'll face a disturbingly high probability of unemployment.
If you would like to further your studies in statistics, we recommend the accompanying...
And some jerk plowed right into me. I'm okay, but it's going to cost a fortune to fix the car. At least I have insurance. You know, it's a wonder that insurance companies stay in business when they've got to deal with things as unpredictable as car accidents. They survive by taking advantage of a statistical concept we'll learn about in this program, the law of large numbers. We'll also learn rules for adding and multiplying the means and variances of random variables. We'll meet one of the most widespread types of probability distributions, the binomial distribution. And we'll learn simple ways to calculate the mean and standard deviation of binomial distributions. Insurance companies deal in all kinds of random events, fires, floods, car accidents. The companies can't predict when someone will file a claim. But if the pool of policyholders is big enough, they can predict accident rates with surprising accuracy. This is like coin flipping. We can't predict the next outcome, but we can predict a long-term pattern. The law of large numbers is a way of defining this phenomenon. Since we know the probability of getting ahead is 50-50 on every toss, if we flip 4 coins many times, the mean number of heads will approach 2 in the long run. And that's what the law of large numbers says. Stated formally, the law says that the mean result of a large number of independent trials comes close to the true mean of a distribution. Now, many people expect even short sequences to have the same regular pattern that's predicted for the long term. But we know that's not always the case. For example, because of random variation, it's possible to get 4 heads out of 4 coin tosses. But people don't understand randomness very well, and so when strings like that happen, they think it's meaningful. This misperception is called the myth of small numbers. You can find those who believe it, as well as those who've challenged it with scientific research in the world of basketball.
Once you get a streak going, it just seems like you can hit a shot with your eyes closed.
It's a great feeling when everything is going right. You know, there's no feeling like it.
When you experience success, it breeds more success, and you make a couple shots or spectacular plays, and you just feel it coming, and you just feel that, hey, there's no way I can miss tonight. Players believe that you make several shots, you feel confident, you become relaxed, you get in a groove, and almost any shot you're going to put up is going to go in. Players describe it as the basket seems huge. Our empirical question is that the case? If you've made several shots in a row, are you more likely to then make your next 1, 2, or 3 shots than if you've missed several shots in a row? We started with the simplest step first, was to just get a hold of the field goal statistics from all games played, or at least all home games, from the Philadelphia 76ers during a real NBA season. And we just looked at the distribution of hits and misses. Does making a shot tend to make you ever so slightly more likely to make your next shot? There is no positive correlation between successive shots. In fact, there's a slight negative correlation. And what that means, translated into a more intuitive statistic, is that the probability of making a shot after having just made your shot isn't greater than after having just missed your shot, which is contrary to what all basketball players, and in fact what I believed up until that time. Now you might argue that, well, maybe there's something like a hot hand that exists, but it's masked by a bunch of other things and it just doesn't show up in the data. For example, maybe it's the case that a hot player takes more difficult shots. So the player would be more likely to make a shot of given difficulty, but that is perfectly covered up by the fact that they're taking more difficult shots. So we've got two things going on that work in the opposite direction. Free throws in many ways provides us with a natural experiment to examine that very question, because they're usually shot in pairs. They're always shot from exactly the same distance, so there's no change in the difficulty of the shot. And there's no defensive pressure. And we look at 2 full seasons of Boston Celtic free throw statistics, and we find players are not any more likely to make their second shot after making or missing their first. The outcome of the second shot is independent of the first shot. Some people object to this research by saying that we're dismissing basketball as nothing but chance, and nothing could be further from the truth. This does not in any way take away from the beauty or complexity of the game.
Unlike basketball, in statistics, it's the long term we care about. The law of large numbers helps us calculate long-term outcomes of random variables. In many cases, it's important to be able to combine information from 2 random variables. Suppose for a minute that we've just won the lottery and we're faced with the pleasant task of deciding how to invest the fortune. For simplicity's sake, we'll decide whether to put the money into the stock market or U.S. government treasury bills. Since the rates of return on stocks and T-bills vary unpredictably over time, it's not easy to decide. Let's take a close look at each option. Here's a relative frequency histogram for the average rate of return on common stocks over the past 30 years. We'll call this random variable X. You can tell immediately that the variation is wide, from a loss of 15% to a gain of 43%. You can also see that the mean is relatively high, about 14%. Now here's the distribution for the rate of return on T-bills. We'll call this random variable Y. The variance is much smaller. In fact, not once in 30 years did people lose money in T-bills. But the mean is also smaller, about 6%. Now, since we've heard that we shouldn't put all our eggs in one basket, we'll decide to put half our fortune in stocks and half in T-bills. What rate of return can we expect? That's the same as asking, what is the mean of the sum of 2 random variables? Before we do that, let's learn some basic rules. The formula for the first one looks like this. It shows that adding any number a to all the values of the random variable x gives you the same mean as adding a to the mean of x. Likewise, multiplying all the values of x by any number b gives you the same mean as multiplying the mean of x by b. In other words, if you add or multiply all values of a random variable by the same number, you simply add or multiply the mean by the same amount. Of course, the same is true for subtraction or division. The second rule says that the mean of the sum of the random variables x and y equals the mean of x plus the mean of y. We'll use both rules in finding the expected rate of return on the investment of our fortune. Since we divided our money in half, the rate of return we get is 1/2 x plus 1/2 y. The mean rate of return for the combined investment is 1/2 the mean of x, stocks, plus 1/2 the mean of y, T-bills. That's 1/2 times 0.14 plus 1/2 times 0.06, which gives us a combined rate of return of 0.1 or 10%. That relatively simple calculation illustrates both our rules. First, we multiplied each of 2 random variables by a constant. In this case, both the constants were 1/2, and then we added the resulting products. Now, why not just put the whole wad into the investment with the highest return? Well, there's a little more to it than that.
The New York Stock Exchange is home to some of the world's most serious investors.
So, 2 plates at 6, chicken sauce, $60. 1,500 pencil shake at 7/8.
Wheaton College is also home to some serious investors. Well, pretty serious. Most of them are found in John Gilday's corporate finance class.
You're each going to have $10,000 to invest. Okay, and we're going to play this game for 2 months. And whoever finishes with the most money after 2 months gets an optional final. Might not seem like a lot now, but come Christmas time when all your friends are shopping and you're sitting here studying for a corporate exam, it's going to seem like a lot then. So,
in Professor Gilday's investment game, there is only one restriction. Students must put their money in at least 3 of the 5 different types of markets: stocks, mutual funds, foreign exchange, commodities, or a money market fund. Halfway through the semester, they can change strategies, selling part or all of their old portfolios and buying new ones. Before the students begin planning their strategies, Professor Gilday gives them some advice about diversification.
another investment might be perfectly negatively correlated with this stock or this investment and have a return that looks like this. So if the game were to end at time period 1, you would want to be up here. You would want to be holding with stock B or investment B. You don't want to be down here. You don't want to be in investment A. So if you don't want to take a chance on either being up here or down here, what you could do is diversify. Put half your money in investment A, half your money in investment B, so that your expected return, do this in a different color here, is going to be in between there. It's going to look like this. It's not going to have any risk involved because these two investments are perfectly negatively correlated. When one goes up, the other goes down. The expected return is going to be the average of those two.
So within each of the markets that they invested in, students had a choice. They could diversify and play it safe, or they could put all their eggs in one basket, taking the risk of either winning big or losing big. It is 1 month into the contest. Betsy and Michelle are evaluating their initial investment strategies and deciding what they'll change.
I think I'm going to save it because it's gone way down. Yeah, since we invested in everything and reinvesting in stocks. I didn't do well. No, you should invest in currencies. Yeah. Foreign currencies, because I bought the Swiss franc and I bought the yen and they went up. I'm not keeping all 4,000.
Betsy had initially put a lot of her money in government bonds, in platinum, and in wheat. Now she's thinking about investing more heavily in the currency market.
30-day forward here. I don't think my portfolio is really well balanced. I think I've gotten more risky than other people in the class. I stand to lose a lot of money if the market turns against me. And if it doesn't, then I'll do really well.
It's the end of the semester. Many strategies have been tried. Most have failed.
I put my money in 3 different stocks, 3 different funds, and the money market. I didn't diversify all that much, but I did a little bit. I lost $350. I diversified a lot. I put my money in 20 different stocks, in 2 commodities, and in mutual funds.
How'd you do?
I lost $200. I lost the most out of everybody. I lost about $600.
If you had all your money in the American Stock Exchange, that index was 301.63.
The reason diversifiers and non-diversifiers alike lost money is that the stock market in general did poorly during these 2 months.
Wasn't a good time to be in the stock market.
But another pattern was noticeable. Neither the big winners nor the big losers diversified their investments. Most people in the middle, on the other hand, did diversify. They had less risk, and they tended to do what the market did, go down a little. Betsy, with her risky portfolio, came out ahead.
The winner was Betsy. We all started out with $10,000. Betsy ended up with $10,342.95.
Going into the second period of investing, I was behind a few people, and I didn't expect to catch up. I'm pretty glad I did. I don't have to take the final now.
What did Professor Gilday mean when he talked about the risk of different investments? Risk in this case translates into variation. The rate of return on stocks, for example, fluctuates far more than for T-bills. Let's look at those two distributions again. Our measure of variation is sigma, the standard deviation. You can see that the sigma for the T-bill distribution is small, about 2%, but the sigma for the stocks is about 8%. Now we're going to learn some rules for working with the standard deviation of random variables. For simplicity, we're going to talk in terms of variance instead of standard deviation. After all, you can always get the standard deviation by taking the square root of the variance. The first rule is adding a fixed number to all the values of your variable has no effect on the variance. The equation says that if we create a new variable by adding a number a to a random variable x, the variance of this new variable is the same as the variance of x. The second rule is that multiplying all values does change the spread. If we multiply x by b, the variance of this new variable is b squared times the variance of x. That's because the variance is the average squared deviation of the x values from their mean. Finally, the variance of the sum of the independent random variables x and y equals the variance of x plus the variance of y. If the variables are dependent, the situation becomes more complex, and the simple addition rule doesn't apply. The rules for means and variances apply to any probability distribution. That's very helpful, but one type of distribution occurs much more frequently than others and deserves special attention. A great many situations involve repeated trials in which there are only two possible outcomes. For example, coin flips or yes-no responses in opinion polls. In such cases, it's traditional to call one outcome a success and one a failure. We're usually interested in counting the number of successes or failures. The distribution of counts like these forms a specific type of discrete probability distribution, the binomial distribution. Binomial distributions are easy to spot once you know these distinguishing traits. There should be only two possible outcomes. In addition, there should be a fixed number of independent trials, and each trial should have the same probability of a success. The conditions for binomial distributions may seem awfully restrictive, but actually these distributions are quite common. For example, in looking at how many children in a family will inherit a genetic disease.
Shannon Leslie and his mother Luanda have come to the hospital for a checkup. Shannon has sickle cell anemia, a genetic blood disease that strikes 1 in 400 newborn black children in the U.S.
Have you had to miss any days from school? Yeah. Yeah, how many? 30.
The disease causes great pain, life-threatening pneumonia, and chronic organ damage and failure. There is no cure, only treatment for the symptoms. In sickle cell anemia, the normally round red blood cells are distorted into sickle shapes, which keeps them from carrying critical oxygen through the body. Like all genetically determined traits, the two genes that carry messages for the red blood cell are inherited, one from each parent. Normal blood cells have two A genes. Sickled cells have two S genes. In families like Shannon's, the parents have one copy of each. Although they are trait carriers, they do not have the disease. Each of their children, however, has a 1 in 4, or 25% chance of receiving both S genes. There is a 75% chance of inheriting any of 3 other combinations and not getting the disease. This fits the binomial mold. Each child inherits the disease or is well. Because the parent's genetic makeup never changes, these odds are constant for each pregnancy. Many trait carriers, though, are unaware of the risks they face.
Since the individuals who carry the trait are totally asymptomatic, have no anemia, have no clinical problems, they would never know they were carrying the trait unless somebody was specifically looking for it. The reason that it's important for people with sickle trait to know that they do is because they need to know whether or not a child that they are going to have is a candidate for having sickle cell anemia. Any complaints? No. Okay. Any suggestions? No. You want to get out of here? Yeah.
Luanda and her husband Willie didn't know they were trait carriers until their second child, Sharonda, was diagnosed with sickle cell as an infant. Now they have 6 children. Sharonda, Shannon, and Shane all have sickle cell.
It's really hard to explain. It's just something, like any mother or any parent when you know that your child has an illness or whatever, it's always going to be on your mind. I can see the character in my children. I can see them becoming more loving to one another. I can see them becoming responsible.
What does focus mean? You focus on my work at school.
And even through the pain, they would talk, laugh, even through the pain. So I said, Lord, I thank you. It wasn't a bad deal after all.
When starting their family, the Leslies had no experience with the statistics of sickle cell. Today, increased screening is identifying more couples like the Leslies, and genetic counseling is helping them to face the consequence of their genetic makeup.
Circus ponies are carrying signs. What signs?
Michael and Marie have one child with sickle cell and one without. They've come to counseling to evaluate their future odds.
Sean has sickle cell disease. My daughter doesn't have sickle cell disease anymore. Any of my other kids have sickle cell because Taisha came out all right.
Since you know, by having a child with sickle cell disease, that you're both carriers for sickle cell trait, you know there'd be a 75% chance that the child would not have...
It's hard for people to understand that one child's outcome doesn't affect the odds for the next. That's why counseling plays an important role in a couple's chance to make informed decisions. The statistics provide the factual understanding, but it's up to the individuals to decide how to use and interpret the numbers.
Nobody should be giving any kind of directed counseling making a decision for them, because nobody, no health professional, nobody but the two people involved really know what's best for them.
The genetic counselor has the responsibility for making sure that the couple understands something about the statistics, knows how to work with those numbers and how they apply to their particular situation, and in sharing in the couple's feelings about themselves, about childbearing, about the future, what it will hold, and when those two important elements are brought together successfully, then the couple can really reach an informed decision that emotionally is good for them and will be good for a future child of theirs.
Give yourself a hand. Yay! You have to clap for yourself. You did great.
The genetic situation in the Leslie family fits the binomial distribution. There are only two possible outcomes, a sick or a healthy child, and the outcome for each child is independent. We know that the probability of having a child with sickle cell disease, if both parents are carriers, is 0.25. We'll look at a probability histogram of sickle cell anemia in families with 6 children. Binomial probabilities are calculated with a complicated formula, but you don't have to worry about the arithmetic. The y-axis of our histogram is probability, and the x-axis is the number of sickle cell children in a family. The axis runs from no children with sickle cell to all 6 having the disease. It's easy to read this histogram. The probability of having 3 children with the disease, for example, is 13%. But public health planners also need to know the mean of the distribution. Fortunately, that's a piece of cake. The mean mu is simply the number of trials times the probability of an individual trial. In our example, in other words, the mean is 6 times 0.25, or 1.5. That's the mean number of sickle cell cases in families with 6 children, where both parents are carriers. Finding the standard deviation of a binomial distribution is also a snap. Here's the formula. Multiply the number of trials n by the probability of a success on a single trial, p, and 1 minus that probability, 1 minus p. That gives us the variance. So to get the standard deviation, we take the square root of the whole thing. In families of 6 children, then, we need to take the square root of 6 times 0.25 times 0.75, which equals 1.06. This binomial distribution has a mean of 1.5 and a standard deviation of 1.06. The rules for finding the mean and standard deviation of binomial distributions are very handy. Just remember that they're only good for binomial distributions. Now, as I said, you can calculate probabilities for specific outcomes in a binomial distribution using the binomial formula. It turns out that there's another and easier way to calculate many binomial probabilities, but you really have to see it to believe it.
This strange apparatus has a strange name. It's called a quincunx, and it models the binomial distribution perfectly. Each time a ball hits a peg, there's only two ways it can go, left or right. It has a 50% chance of falling in either direction. The next row of pegs is independent. Again, the same odds apply. The balls make their way down the quincunx and finally into the bins, which record the total number of falls to the left and falls to the right. The balls in the far right bin, for example, fell to the right every time they hit a peg. There aren't many of them. The balls in the middle bin fell right half the time and left half the time. This bin has the most balls. Not too surprising, since we know that the probability of falling right or left is 50% at each peg. The shape here is looking awfully familiar. It's nearly normal. And the amazing thing is that quincunx will form this shape every time.
Binomial distributions are often nearly normal, and that means we can calculate probabilities using the tools we've already learned for working with normal distributions. Let's take a closer look at this distribution. The probability P of a ball falling one way or another off a peg is 0.5, and the number of rows of pegs is large. In general, when n is large, the binomial distribution will be close to normal regardless of what value P takes. The distribution will be nearly normal if P is 0.5, even if n is small. But for small n's, the distribution becomes more skewed as P gets closer to either 1 or 0. So when n is large, or when P is close to 0.5 in a binomial, you can generally use normal calculations to find probabilities. On top of that, you can use the two easy formulas we've learned to find the mean and variance of other binomial distributions. In this program, we've gone from the general to the specific, from the law of large numbers, which holds for all random distributions, to the binomial distribution, which describes a particular class of discrete random variables. Now, I've got to run. I have to get my car to the shop.
If you would like to further your studies in statistics, we recommend the accompanying course package, which includes the text Introduction to the Practice of Statistics, as well as a study guide linking the programs to the textbook. The complete package is available for $69. To order yours, have your Visa or MasterCard ready and call Toronto 445-5333. From outside Toronto, call 1-800-663-1800.
We are trying to change from the notion of working, i.e. coming to work from 9 to 5, hustle a little bit when the boss is around and not getting drunk, to the idea of literally everybody involved in continuous improvement all the time.
The Tom Peters Experience, Thinking in Action, and Working with Assertiveness are 3 programs that can help you be more competitive in your business dealings. All 3 programs offer special learning packages. Find out more information by calling the numbers on your screen. Australian journalist Murray Sale rides the Trans-Canada train, searching for the true Canadian identity.
People that goes away from the fire, I don't think they should have to go away. No,
I think that's a crime.
For me, it's my country is Quebec. It's not Canada.
So who is the Canadian?
I guess anybody who lives here is a Canadian.
Well, I'm a Canadian.
The Last Train, a cross-Canada journey, tonight at 9.
A police officer takes the law into his own hands with astonishing personal results. Philippe Moret and Isabelle Huppert star in Coup de Torchon, Friday at 10, 9 Central on J. Scott's Film International.
You're watching TVO.
Welcome to TVO Home Studies. Next, we present Against All Odds, a university-level statistics course. The accompanying text, Introduction to the Practice of Statistics, is part of the course package. It provides contemporary instruction on data analysis. You'll also receive a study guide, which links the programs to the text and includes reading lists, problem assignments, a self-test, and sample examinations. At the end of the program, we'll tell you how to order the course package. Now, Against All Odds, Inside Statistics.
It's what makes gambling so exciting, even addicting. People flock to casinos knowing there's a chance they could walk away rich. But everyone also knows that casinos make money, and lots of it. How can that be? Casinos have perfected the art of using randomness and probability. I've turned my office into a mini casino because in this program, we're going to learn the statistics behind the casino owner's success. Information that goes way beyond gambling. We'll see that analyzing the distribution of sample means can help us understand random phenomena like roulette. We'll learn about the central limit theorem and how it makes predictions of probabilities possible. And we'll move on to see how control charts help businesses turn out better products. Regardless of your opinion of gambling, casinos are statistical gold mines. Whether they're pulling slot machine handles or praying for a blackjack, all the bettors are immersed in a sea of probabilities. Let's see what we can learn by looking at one of the oldest casino games, roulette. The wheel has 38 slots, 18 black, 18 red, and 2 green, which are labeled 0 and 00. When the wheel is spun, the ball is equally likely to come to rest in any of the slots. Now, there are lots of ways to play roulette, and one of the most common, you bet on color. For example, red. If the ball lands in one of the 18 red slots, you win, and the casino pays you whatever you bet. If you bet $1, you win $1. If you bet $100, you win $100. Of course, if the ball lands in any other slot, you lose whatever you bet. Now, since there are equal numbers of red and black spaces, it's clear that your chances of winning are close to 50-50. It's those 2 green slots, 0 and 00, that tip the scales slightly out of your favor. If the ball lands there, you lose whether you bet red or black. Let's see what outcomes a bettor can expect over the long haul in roulette. In statistical terms, we want to find the mean of the random variable. As we learned before, to find the mean of a random variable, we multiply each outcome by its probability and add them together. In this case, let's suppose I bet $1. The 2 possible outcomes are either a win of $1, which is 1, or a loss of $1, which is -1. My probability of winning is 18 out of 38, or 0.473. That's the 18 red or black slots over the total number of slots. The probability of losing is 20 out of 38, or 0.526, which reflects the addition of the 2 green slots. To find the mean, we simply multiply my probability of winning, 0.473, by 1, then multiply the probability of losing, 0.526, by -1. Adding the two gives us minus 0.053, or minus 5.3 cents. So in the long run, a bettor can expect to lose 5.3 cents for each dollar bet. That's important for the casino owners. They're in the business for the long term. But the average gambler has a different perspective.
Most of it's luck, but the skill is about 10%. If you know the 10%, normally you'll win.
You have to quit right while you're ahead because that's the only way you'll beat the game. If you keep playing, you win, and you keep playing, then you're a fool.
I'll probably keep playing, try to win as much as I can.
In Atlantic City, the name of the game is gambling. And today, it's a safe bet that thousands of visitors aren't flocking here for the weather. Gamblers arrive knowing that inside the casino it never rains, but sometimes, if they're lucky, it pours. The gambler enjoys the exciting surroundings and the fun of trying for the lucrative jackpots. But for the casino, this is no game. It's a serious business. The payoff for a casino also depends on large numbers, but of a different sort.
In casino gaming, the house edge is very small, unlike the lottery, where it's like 50%. We have a percentage advantage in most games that is less than 1%. But by attracting thousands and thousands of people a day, in fact, some days we think we get as many as 50,000 people walking into an Atlantic City casino. That small edge starts to eat in, and we start to generate revenues, which average in an Atlantic City casino about $700,000 per casino per day.
The casinos create a world apart from the real world, a lush environment in which people enjoy playing and staying all day and all night.
We're looking to attract, retain, and return customers to Resorts International. We'll attract them through newspaper ads, clip and brings. People will clip out ads in the newspaper, bring them in here for redemption. Simply present the clip and bring at our promotions booth, and we'll give you a credit up to $20 in food. We'll do entertainment specials, 2-for-1s, free tickets to returning customers for our review or our Superstar Theater. We'll do drawings on the floor to give away cash prizes.
The promotions not only attract customers to the casino, they can also be designed to encourage gamblers to place more bets on the games or in the slot machines.
In addition to the $25,000 top jackpot that the machines offer, you can win this 1988 Porsche. Now, this is an innovative promotion. It's something new, it's something fresh, and for instance, we may attract customers who normally may not play slot machines, but they'd like to take a shot at winning a new Porsche.
Once on the floor and playing, the gambler looks to cash in on the very unpredictable outcome of any individual bet. Indeed, in the short term, the player stands a good chance of winning a healthy return on the money he's bet against the house.
When a player first comes in, his chance of beating us is about 50-50. When he's ahead, he can walk away. We have no way to bring him back to the table.
While at the table, though, the more bets placed by a gambler, the more likely he is to lose over the long term. So the casino counts on the individual who tries to get too much of a good thing.
A smart gambler will come in and bet the maximum he can afford to lose on one roll and walk away either a winner or a loser, because the house edge has only been 0.5% on that particular bet. So he's got a 49.5% chance of winning. We've got 50% chance of winning. Most players, though, enjoy the fun of casino gambling, and they want to stay at the table for a longer period of time to enjoy that, and that basically gives us a bigger edge.
Meanwhile, those who have done battle with that cutting edge are back in the outside world, ready to head for home.
I broke out about even. It was fun.
How'd you do? Lost my shirt. You what? Lost my shirt. You gonna come back? Sure. Come back all the time. Lose my shirt every week.
I won a little bit. About $50.
That's a lot.
Oh, no, it's not. I'll be back next week.
Yeah?
Maybe next week I'll do a little better. This is my 40th course trip.
Everything dies, baby, that's a fact. Maybe everything that dies someday comes back. Put your makeup on.
casino owners pay a lot of attention to the long-term mean, gamblers focus on the variation of individual bets. Let's take a closer look at variation, again with roulette. What we want to find is the standard deviation for single bets. We'll start by finding the variance with this formula, which we've seen before. We plug in our value for mu, which is minus 0.053, and our two outcomes, 1 and minus 1. Then we plug in their respective probabilities. We find that the variance is about 0.997, and so the standard deviation is a square root, or about 0.998. For single bets, in other words, there is a huge standard deviation, 99.8 cents per dollar bet. But most gamblers bet repeatedly, so the standard deviation of single bets doesn't tell us the whole story. To explore this further, we're going to look at something new, the average outcome of a series of bets. Suppose we kept track of a gambler's wins and losses over the course of 50 $1 bets. For example, let's say a gambler was lucky, and at the end of his string of 50 bets, he won $10. His mean winnings per dollar then would be 10 over 50, which is 0.20 or 20 cents. We can restate the situation by labeling the outcome of our bets as X. The mean result of a series of 50 bets would be our familiar X bar. We know that if our gambler placed another series of 50 $1 bets, he probably wouldn't get the same average result. Maybe he'd lose an average of 4 cents per dollar. In other words, the mean outcome, X bar, will vary from sample to sample. What would happen if we repeated this trial of 50 bets a large number of times? Let's do that and keep track of the mean of each trial with a histogram. You can see that the x-axis ranges from a mean loss of $1 per bet to a win of $1 per bet. The y-axis is probability. As more and more trials are performed, the mean win or loss, X bar, varies randomly, but soon a pattern emerges. After a large number of trials, we've produced the distribution of X bar. As before, we can describe this distribution with a smooth curve. One thing about this distribution of X bar is immediately apparent. It's roughly normal. This is a remarkable fact, so remarkable that it has a name, the central limit theorem. The theorem says that the distribution of X bar becomes more and more normally distributed as n, the number of observations, increases, even if the population distribution is skewed. Let's see what light the central limit theorem can shed on roulette. First, we need to know the mean and standard deviation of the distribution of X bar. Here's our distribution of the mean of 50 $1 roulette bets again. The mean of this distribution is the same as the mean of the population of individual bets, negative 0.053. The standard deviation of X bar, designated this way, is the standard deviation of the population divided by the square root of the number of observations, n. X bar is always less variable than individual observations. The variability of X bar gets smaller as we take more observations. It's this fact that distinguishes the experience of the gambler from the experience of the casino. Let's see how variation decreases as more and more bets are placed. We saw before that the standard deviation for single bets was large, 0.998. Using our formula, we find 0.998 over the square root of 50, which equals about 0.14, or 14 cents. That 14 cents is a far cry from the 99.8 cent deviation of single bets. We know from the 68, 95, 99.7 rule that virtually all of our gamblers' results will fall within 3 standard deviations of the mean. Multiplying our 14-cent standard deviation by 3 gives us 42 cents. So a gambler can expect an average result between a loss of about 47 cents per dollar bet to a gain of about 37 cents per dollar bet. Multiplying each of those amounts by $50 shows that a gambler placing 50 $1 bets can expect a final result somewhere between a loss of about $23.50 and a gain of $18.50. That's why gambling is exciting, even for 50 bets. The outcome is highly variable and broad enough to encompass winnings. But what happens if we make 1,000 bets many times? The distribution of X bar for 1,000 bets looks like this. The mean is still centered at minus 0.053, but the standard deviation has shrunk to a mere 0.03, or 3 cents. You can see that the bulk of the curve lies in the loss side of the x-axis, meaning that while there's still a chance a gambler will end up a winner after 1,000 bets, it's a mighty slim chance. Now let's look at things from the casino's perspective. If 100,000 bets are placed, the distribution of the mean result is nothing but a spike with a minuscule standard deviation of about 1/3 of a cent. The curve doesn't spread into the realm of a win at all. That's how the casino is guaranteed a profit. Our foray into the world of gambling introduced us to several important statistical facts. We learned about the central limit theorem, which says that the distribution of the sample mean, x bar, will be approximately normal when the number of observations is large. We also saw that the mean of this distribution is the same as the mean of the population from which it was derived. And finally, the standard deviation is the population standard deviation divided by the square root of the number of observations. These concepts are used for a lot more than just understanding the statistics of roulette. The sample mean, for example, is the keystone in the quality control efforts made by most industries. We can see that effort in action by visiting a familiar factory.
Making potato chips is a carefully controlled process. Actually, it's several processes, all involving human labor and complex machinery. So how does Frito-Lay know when and where they have a problem? In the past, a company would inspect the product at the end of the process. But that's a little late to know if something's wrong. There are better ways. Sampling, as we saw in an earlier program, is one way to check on the process as it's happening. But as it turns out, it's only the beginning. Frito-Lay is one of the many American companies to add a new tool to their production line, Statistical Process Control, or SPC for short. It's a way for people directly involved in a process to know when to make changes and when not to. SPC is becoming universally accepted in American business, but it took a while to catch on.
I was a little fearful of the whole thing, not being totally familiar with statistics. It was something new to me, so there was a certain amount of reluctance on my part. But I soon became a believer once we started the process. Our variability from bag to bag diminished. We've probably made a 50% improvement in variability since we've instituted SPC in our operation.
Statistical process control is made at critical control points in the process where you can actually impact the quality of the product. And by setting up statistical control charts or Shewhart charts, you can